Welcome, my friends! Today we will be talking about histograms. A histogram is one of the most common ways to display data that you have gathered, so what better place to start than with some raw data? Here we have the final exam scores out of 100 points for 250 different students. This is just the raw data, and it's kind of a mess. It's hard to say anything useful about the exam scores for the students by just looking at all of the 250 scores in their raw form. One way to organize this data, which also turns out to be the first step in creating a histogram, is to create what is called a frequency distribution. The idea is to segment the data into groups, usually called classes or bins. In this case, I'm going to have 11 classes in increments of 5s, represented by the 11 rows of the table. There are no exam scores less than 45, so I'll start the lowest class at 45 and end the highest class at 100, the maximum score on the test. I will increment by 5s in the middle to create my 11 classes. Next, you will simply count how many exam scores fall into each class to find the frequencies. If we counted the number of scores between 45 and 50, which are partially hidden now by my frequency distribution, we would get 11. The number of scores between 50 and 55 is 15, etc. all the way down. You would probably do this step with a computer most of the time, unless you have a really small dataset. As we have 250 exam scores, the total of all of the frequencies should add up to 250. Now you might be thinking to yourself, aren't we double counting? Each class contains a repeated number. For example, we see 50 in 2 classes, also 55 in 2 classes, which is an issue for every class all the way down. Well, it turns out that you have to make a decision of where to count the repeated values, but you have to be consistent. For example, you might include all of the upper bounds, but not the lower bounds, or vice versa. So maybe 55 is included in this class, but not in this one, and 60 is included in this class, but not in this one. This is the method that Excel uses for classes in a histogram. How you decide to include or exclude values at the margins really isn't all that important. Okay, once you have all of the frequencies, the next step is to calculate the relative frequency or percentage of the whole for each class. We simply take the frequency and divide by the total number of observations. If you add up all the frequencies, you will see that we get 250. So we have 11 divided by 250, which gives us 0.04 or 4.4% for the first class. We have 15 divided by 250 is 0.06 or 6% for the second class, and we can continue this process all the way down for the rest of the classes. Okay, now that we have finished our frequency distribution, there are a few things to note. First, note that in a frequency distribution, each class needs to be of equal length, which you notice is the case here. 45 to 50 is a length of 5, 50 to 55 is also a length of 5, as is every other class. Also note that the number of classes you have should depend on how much data you have. If you only have 20 observations, it wouldn't really make sense to have 11 classes as I do here, as each class would have a very small frequency. There are many methods out there for how to determine how many classes to have in your frequency distribution, but we won't be discussing them in this video. Once you have a frequency distribution, you are ready to create a histogram. A histogram is simply a graphical display of a frequency distribution. Each class is a bar, and the length of each bar is the corresponding frequency. Here is the histogram for our 250 exam scores. There are 11 bars because there were 11 classes in the frequency distribution, and the height of each bar is the frequency. Note that in a histogram, there should not be gaps between the bars to represent the continuous nature of the numbers on the horizontal axis. Now that we have created a histogram, it helps us make some important observations about the data. Notably, we can see that the most common exam score is somewhere between 75 and 80. We also see that exam scores much higher or much lower than the 75 to 80 class become less and less common. Technically, a histogram is a type of bar graph, but we don't use the terms bar graph and histograms interchangeably. A histogram is more specific, as it has the same characteristics every time. There are no gaps between the bars, the horizontal axis represents a quantitative variable, and the vertical axis represents frequency. A bar graph could look something like this. This graph displays the religious affiliation of a sample of 982 people from Michigan. Here, the horizontal axis is the categorical variable of religious affiliation, and therefore is not a histogram. Recall that back in our frequency distribution, we created a column for the relative frequencies. Sometimes, instead of frequency as the vertical axis for a histogram, we will use relative frequency instead. The shape of the histogram will be exactly the same, but we will have percentages instead of counts on the vertical axis. There are 5 main shapes that histograms can take on. The first is what we call mound-shaped symmetric, or normal. This is the case when most of the data falls in the center of the distribution, with less and less of the data falling into the tails of the distribution. The second is what we call a uniform distribution, where any observation inside the distribution is just as likely as any other observation. The third is bimodal. This is the case where there are 2 peaks to the distribution. Then we have the skewed distributions. A skewed left distribution has a tail off to the left. There are many high values in the distribution and less small values. In a skewed right distribution, there is a tail off to the right. There are many smaller observations and less larger values. It's very easy to get skewed left and skewed right distributions confused. Think of the words skew and tail as going together. Wherever the tail of the distribution is where the skewedness is. So a skewed left distribution has a tail to the left, and a skewed right distribution has a tail to the right. Let's think about a few different variables and what distribution shape would most likely accurately characterize the data. Take a moment to pause the video and think about each of these 5 situations, and I'll be back in a moment to discuss. Okay, the first one says the time it takes students to complete a quiz. Most students finish in about 10 to 15 minutes, with fewer and fewer students taking longer amounts of time to finish the quiz. This will be a skewed right distribution. There would be higher bars in the histogram toward the left for the lower values, with a tail to the right for the fewer and fewer students taking a long time to finish the quiz. Next, we have 50 randomly generated numbers ranging from 0 to 100. Well, since the numbers are randomly generated, we should expect an equal proportion for just about every number. That is the definition of a uniform distribution. Next, we have the test scores in a class with several very high-performing students, several very low-performing students, and not many students in the middle. This problem seems to be describing a distribution with 2 peaks, lots of low scores and lots of high scores. When we have 2 separate peaks, we call that distribution bimodal. Next, we have the test scores of students in a high-performing statistics class. Most students receive a very high score, with less students with lower scores. Well, if we have most students performing very well, we would have very high bars on our histogram towards the right side, with lower and lower bars towards the left, creating a left tail. Therefore, this is going to be a skewed left distribution. Finally, we have the most frequently occurring height in adult males at 5 feet 9 inches, with fewer and fewer adult males with heights either higher than or lower than 5 feet 9 inches. This sounds like the biggest bar of the histogram would be right at 5 feet 9 inches, with decreasing bars as you increase or decrease from 5 feet 9 inches. That sounds a lot like a mound-shaped symmetric or normal distribution. Alright, that wraps up our examples and our video on histograms and distribution shapes. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure you subscribe and check out my other videos.